So I'm going to talk about common mistakes made when fitting models to data, which is basically what statisticians do. The colors I chose, not because it's Halloween, but because those are beaver colors. I got my doctorate at Oregon State. I have a master's from Iowa State, so both in statistics. My doctorate's in mathematical statistics. I also have a minor in applied statistics. So that's my background. Why this talk? There's been a lot of press in the last couple of years about bad research, unreproducible research. And a lot of it's in cancer research. There was an article in The Lancet not too long ago. That was in, let's see, The Economist about 2 weeks ago had an article, The Lancet within the last 6 months, on how a lot of research, when they look at it, it's not reproducible. And so that's not good. I mean, that's the gold standard of research, is it's reproducible. So if we do a finding here, someone at Penn State does a finding, it should be comparable to ours. If it's not, we've got a conflict. Science isn't working. Who's right? So that's one of the... we're in trouble here. Start over. Might be the world's shortest talk. Okay. So we've all heard, lies, damn lies, and statistics. Statistics has a bad rap. This is attributed to Disraeli by Mark Twain, but nobody really knows whether Disraeli ever said this. It's been around for a long time. This one I kind of like. This kind of describes the way I think of statistics. Now, when physicists do mathematics, they don't say they're doing number science. If you're analyzing data, you're doing statistics. You can call it data science, informatics, analytics, whatever. But you're doing statistics. That's what statistics is about. Now, conducting data analysis, it's not a fast process. It's like drinking a fine wine. It's important to swirl, sniff the wine, unpack the complex bouquet, appreciate the experience. Gulping wine does not work. So, in my career, a lot of people call me up on the phone, and they want an instant answer. Can't give you that. That's not the way statistics works. So those are some of the things I'm going to be looking at. So what is statistics? We like to think of it as the science/art of describing populations in the presence of uncertainty. We don't have the whole population at our disposal. We have a portion of it, a sample. So that's the uncertainty we're generally working with. Science, yeah, it's mathematical science. But there's a lot of artistry in it. There's a lot of interpretation. There's a lot of artwork in getting good data. You should know statistics does not provide answers. It never has, it never will. It gives you information. It plays a supporting role. It filters the data and it says, here's what the statistics say. It's not the answer. It can't give you an answer. It's based on a sample, not the entire population. It can give us very convincing evidence. That's what we're hoping for. But it's not going to provide answers. It may provide useful information about the answers. And we're using it for empirical support. We're good scientists. We've thought this out. We pretty much know what should happen, hopefully. We wouldn't do this study if we didn't know what was going to happen or expect this to be a new research hypothesis we can support. So this is backing us up. It's not proving our hypothesis. So just the basics, this is the old get up on your soapbox and preach lecture. So we go into the three phases. We're going to do a statistical analysis. The most important is the planning stage. This is where most of the errors are made. In my career, I've done lots of consulting, lots of statistical analysis. 95% of it comes to me as a data set. Exactly the wrong way research is supposed to work. I didn't have any input on how the data was collected. I didn't have any input on the data structure, which is really important when you analyze statistics. So that's a big component of any research project, if you're going to use statistics. So I'm talking about research that relies on the data. It's not a deterministic system. You want the data to support your research hypothesis. So then, after we get that planned, we'll go and talk about analyzing the data. And then there's always the summary and interpretation. Statistical analysis, computers are great these days. They'll do it all for you. But do the computers know what they're doing? Do they know the fine aspects of your data set? Do you know what to tell the computer to do? So the statistical analysis is not that, it's not a trivial step. If this was really easy, if statistics was something we could all do, there wouldn't be stat programs, PhDs in statistics, all over the country at all the top research schools. This is not a trivial process. So, in the planning stage, if we're going to use statistics, the researcher's got to do something up front. You've got to do your job. So you've got to identify a clear set of research objectives. You know that. That's critical, though, because the statistics are going to, the sampling plan is going to have to tie to this. So you've got to have this well thought out. You have a well-defined population of interest. Just basic ideas. Well-defined response variable. I've had people come to me, and they can't tell me what the response variable is. The output variable, the dependent variable. You need to have that. That's got to be meaningful. It's got to represent what's going on in your research. If you don't have it, we're in trouble. All of the sources of variation, which is really the variables. Which variables affect the response variable? So there's some that you're planning on measuring. Those are the explanatory variables. Very important. Then there's some other ones we have to worry about, called confounding variables. Those are the external variables you didn't measure, whose effects on the response are not distinguishable from the explanatory variables you did measure. Critical component to take care of confounding factors. It could be as simple as you've got students doing your measurements for you. Two different students measure, and they measure in different ways. So there's a student effect. You don't want that. That's a confounding factor. We have to worry about that. Have to train your students to do it very similarly. It could be, a confounding factor could be you do things in a greenhouse. There's different light gradients in a greenhouse. If you have all of these one plants treated on this one side and these on the other side are not treated the same, you have a light gradient that's going to be a confounding factor. So we have to worry about sources of variation, and we have to control for them. Some of them we like. Those are the treatments we're looking at. The explanatory variables, what we think causes change in the response variable. And then the ones that we really worry about, the confounding variables. Okay, you have to formulate your well-defined research hypothesis, and this is not what it really sounds like, because at this point we have to think about how is the statistics going to come into play. You want to say new improved Tide is better than old unimproved Tide laundry detergent. Okay, there's a research hypothesis. What is the statistical parameter you're going to compare? How are you going to do this? What do you mean? The mean cleanliness factor, cleanliness recording for new improved Tide is better than the cleanliness measurement for the old unimproved? Median? 25th percentile? So when we get to thinking about we're going to use statistics, you have to think about these things. Okay, what's the statistician going to do? What's he going to want to know? Okay, so that's where you bring in the statistician. You've done all, you know what you're going to do. And you know what you want to do. But you need data, so you consult a statistician. We've got a statistics department here. There's 3 PhD statisticians here. So we'd be happy to help you. Write us into your grant. We'd love that. So sentiment of most statisticians: to consult a statistician after an experiment is fission is often merely to ask him to conduct a post-mortem examination. He can perhaps say what the experiment died of. 5%, 10% of the people that come to me with data I won't do anything for. I do exactly this. I tell them I can't analyze that. You don't have the right data structure. I can't help you. Statistics won't work that way. It doesn't just work on data. It works on data structures. So it's critical that we get the planning done correctly. So now we bring in the statistician. They're going to help you develop a sampling plan that gets you good data. At least that's the goal, and we have plans that, almost certainly get you good data. We can be unlucky. We'll control for confounding factors. Now, this can be a very painful process. This is why you guys don't come to us, because we're going to ask you lots of questions. You're going to want an answer right now. I can't give you an answer right now. This might take weeks. 3 meetings, where you give me some information, I get up to speed on what you're doing, then I get some more questions. It's a slow process. It doesn't have to be that slow, but it's not something that you come to me, I'm going to know exactly how to do this. Sampling is incredibly difficult. Getting good data, and that's the most important part of your research. Before we get data, I can tell you exactly what I'm going to do with it. I've designed a structure where I can analyze it. If you don't have the right structure, this goes away. You come to me with data, I didn't have any input on what the structure should be, there'll be things I can't do. So we're doing this all up in front. We don't have any data. This is the planning process. The nice thing about statistics is that we have measures of reliability. If you want to estimate some parameter, I can tell you how accurate your estimate is. I can give you a measure of reliability. If you do a hypothesis test, I can tell you how accurate your hypothesis test is. Every statistical procedure has reliability measures put into it. Those are very important. Those affect the sample size. If you come to me with data, you didn't consult me in advance, you may not have enough data to detect the significant difference you wanted. If you come to me in advance, we can design your sample so that you will have the right sample size to be able to detect this distance, which you thought was a practical difference. Okay, so now we cut you loose. We're tired of each other. We need a trial separation. The researcher collects the data. So I've outlined how you do it. We're going to use random samples. We're going to use what's known as a probability sample. Probability sample is just a sampling plan where we know which samples are possible and we know the probability that they're selected. There's lots of different sampling. We can design a sample to fit hopefully any population to get us representative data. Random sampling is critical. It removes sources of bias. It also allows the statistics to work. All of the theory is based on having a random sample. If you don't have a random sample, you're throwing out all the theory that you want to use. So we need random samples. Okay, so you've got your data, you come back, you call me, and it's like, oh my God, that was such a nightmare planning this. Now I got to analyze it. We get together, we analyze it. Often I do the analysis. I've got the computer packages. I know exactly what I'm doing, run it through. It's done as we described. Sometimes in the collection phase, things go wrong. You have missing values. It can be a real problem. You might have some strange data we need to talk about. So I would recommend that I'm involved or a statistician's involved in your research. The formulas look simple. The computer tells you, oh, this is wonderful, you just do this. But statistics is changing rapidly. When I was at Iowa State, 1978 to 80, computers were just becoming available. When we had categorical data, we did contingency tables. Now nobody does contingency tables. We do models. It's changed. Computers have made things available to us now that we couldn't do 20 years ago, 30 years ago. Bayesian statistics. Maybe you've heard about Bayesian statistics. That's really hot now because it's based on the computer. In fact, new statisticians coming out are almost all going to be in the Bayesian fields. Their frequentist field, still important, but it's not as important as it used to be. The big data sets, the microarray data sets, huge data sets, the Bayesian field of statistics is taken care of real well. All right, so I've done it. We get back together, we meet, we talk about what's going on, how do you interpret it. You've got a non-significant test. What does that mean? Is that good? Is that bad? Sometimes it's good, sometimes it's bad. So if you come to me with the data, it's probably bad. And then, the thing I always think about is it's not a race. It's really better to do it right than to race. And what's the chance someone's doing the same thing you are and they're going to beat you to it? And if they do, then you get into, a conflict like Newton and Leibniz did, and you can have a historical battle. It's great. So that's what statisticians want. This is what we want. If you're going to involve us, you're going to use statistics, get us involved, we'll help you, and we'll do it right. Doesn't mean that I'll know exactly what to do at the start. There's a lot of different sampling plans, a lot of different things that you guys do that aren't classical statistics that'll take me a little research to find out how to do it right. Okay, big part of all of this is the sample size. And this is a painful one. Because I'm going to come out and I'm going to say, okay, you need 100 observations. And you're going to say, well, my budget only allows me 3. I'm going to say, well, you need 100 observations. You say, well, maybe I can squeeze a 4th. You're not going to get any precision. You're not going to have accurate estimates if you don't have enough data. So how do you know? Oh, you said 100. Well, I can take 5,000. Well, now you're just wasting money. We don't want to do that. It's not necessary. How big a model can you fit? So if you're doing what I'll talk about later, a regression model, if you have 20 observations, you can only have 2 variables in your model. If you've got 100 observations, 7 variables and some other things, we start adding variables to the model to account for different things that we're seeing. You don't have enough data. You need about 10 observations per variable to fit a model. If you're doing, that's in the best case. Sometimes you need about 20 observations per variable. Power. Power is very important. If you're going to do hypothesis tests, which we all want to do, the journals want us to do it. They want us to have a significant result, a p-value less than 0.05. You want to have a powerful test. Power is the ability to distinguish between H0 and HA. Your HA is your research hypothesis, H0 is the status quo. If you fail to reject, so you don't find significance, the power may say, that's okay, you're right. Your hypothesis was wrong. That's what power will tell you. But if you don't have the power, you just take a sample, you don't know what the power is. If you don't find significance, you don't know whether you're right or wrong. And most likely, you're going to be wrong. The probability of making a type 2 error, 2 types of errors in a hypothesis, probability of a type 2 error when you don't find significance is often very high. So we got to have that. Statistical significance. You don't want to take too big a sample so that you can tell the difference between the number 10 and 10 followed by 1,000 zeros and then a 1. That's probably not a practical difference. You've oversampled. You've wasted time and money. So, a big sample is not necessarily better than a small sample. Outliers are unusual points. You get an unusual point. Well, if you've got a lot of data, that point really won't matter. The influence of an outlier is diminished when you have a large sample. If you have a small sample, that point may be very influential. If it's a really bad outlier, there may not be any amount of data that fixes it. We'll come back to outliers. And then the assumptions. Normality is the typical assumption you hear about. Something's normally distributed. That often goes away as the sample size gets large. A lot of the other assumptions don't. So the sample size is critical. And it may be expensive. You come to me and you say, I want this precision, or I want this power, or I want this many variables in the model. I'm going to tell you you need 100. You tell me I can take 25. you're wasting my time. You're wasting your time. It's not worth doing. We need to scale back. Like to have enough data for model validation. We almost never do that. But collect 200 observations, hold aside 50 to check your model against those 50. Build it on 150, check it on 50. We could talk about that. But to me, as a statistician, if you can't afford the appropriate sample size, your estimates aren't accurate enough, you don't have enough power, you can't build the model we want to build, it's not worth doing. So maybe it's in the grant stage. How much money do you really need to do this? Maybe you need to get a statistician involved when you're writing your grant. More pain. And then the old rule that a lot of us learned in our first stat course, n equals 30 is a large sample. That is true for the central limit theorem. The distribution of x bar will be approximately normal when n's 30, almost across the board with distributions. But that allows you 3 variables in a model. That may not be enough observations to have good degrees of freedom in a designed experiment. You may not have enough error degrees of freedom. That's not a large sample. That's an extremely small sample in most cases. So throw that out of your mind. I mean, that's been out there forever, and we need to kill it. Okay. Bad data. Data at hand is always bad. Convenient data is never good. You want a random sample. You don't. I do. I want a random sample. If I took this room right here and said, I'm going to use this as my sample, and I'm going to estimate the mean GPA, get out of class mode, the mean IQ of a citizen of the United States, it'd be a terrible sample. We're a university. We are traditionally the more intelligent people. Our IQs should be shifted up above the mean, which is 100. You know, a lot of people, I've heard it in lectures, you know, mean IQ is 100, so, and it's the median, so half the population is below that, half is above it. So, you know, look around the room, half of these people have IQs below 100. Well, I'm at a math talk, professional math meeting, they're all intelligent people, probably nobody in there has an IQ under 100. So the data at hand, just because it's convenient, generally makes it bad. Okay, so finally to kind of what I wanted to talk about, modeling. So a statistical model, which is basically anytime you have data, you have a model. Even if you're just estimating the mean of a population. Each observation is the mean plus an error. So we always have models out there. It's just a formalization of the relationships between the variables. Often we put distributional assumptions on there. But that's what a model is, statistical model. This is what you have to keep in mind. All models are wrong, but some are useful. George Box, very famous statistician, wrote several books on model building, response surfaces. We're approximating things. What we use in statistics primarily is Taylor's theorem. Taylor's theorem from Calc 2 says everything's approximately linear. You look at a sine curve, it's approximately linear. You're like, oh my gosh, it's got, you know, it's this wave function. Well, if you take a small region, it's approximately linear. And if in that small region it's not approximately linear, then it's approximately quadratic. And if in that small region it's not approximately quadratic, it's approximately cubic. I mean, Taylor's is great, but primarily in statistics we use Taylor's approximation. We've got a response variable we're modeling as a function of these explanatory variables, x1 and so on, and we're just using Taylor's approximation. And we're not really worried about our model being wrong. Is it useful? The world's complicated. If you've found something, you've got a y variable and one x variable, and x explains y almost perfectly, but then you're looking at an awful simple problem. I mean, that just doesn't happen. That's very unusual. Life is complicated. We need lots of variables in our models generally. Now, typical in statistics, we talk about regression models. And all we mean by regression is a conditional expectation. That's all that a regression is. There's lots of types of regression. There's the standard linear regression. You think of a normal error structure. There's logistic regression, which is based on categorical data, Poisson regression. There's proportional hazards. There's generalized linear models. They're all looking at these type of things. Conditional means. Here's the variable we're trying to predict, explain. These are the variables that are doing the explanation. We believe the x's cause changes in the y. So this is a whole variable. We have a whole column of data on x1, a whole column of data on x2, and so on. That's what a regression model is. And there's nonlinear regression, there's all sorts of different types of regression. Okay, so now we want to build a model. So what should you do? You've got this model specified. Well, always in statistics. Look at the data graphically. And this is an interesting step. But what this does, it gets you familiar with your data. Often you see an extreme point, something unusual. That's important to note. Often you don't see anything going on. Typically we look at our data in a two-dimensional plot, scatter plots. Got y on the y-axis, x on the x's on the x-axis. You do them independently. They can hide things. We can't look at, say, a 10-dimensional plot. So we go down to 2 dimensions. And it hides a lot of things. So you just see these blobs of points. And they're like, this x doesn't seem that related to y. Well, regression basically adjusts for all the other x's, and it takes into account the information in all of them. So it's not a two-dimensional picture we should be looking at, but this is an important step. Okay, we fit the model. So we ask the computer, hey, put the equation in, tell it what to do, what variables are in it, fit it. It might be least squares, it might be iteratively weighted least squares, might use a pseudo likelihood function. Whatever, we do that. That's the computer's going to do that for us. Now the critical component is that's not enough. We need to analyze the model. How well is it fitting? Is it even appropriate? So we've got to look at some model diagnostics. And that's the critical part of modeling, is to diagnose, is this a good model? Does it have extreme points? Does it have problems? Is it valid? So models come with assumptions. We need to check the assumptions of the model. Critical. Every model you build has a set of assumptions. Could be, I don't know, I'm not going to get into the technical details, but they all have models. They all have assumptions. You got to check those. You just don't assume these things. You have to, if they're not valid, we've got problems. Okay, outliers. Look for points that your model's not fitting. That can be a problem. Can indicate your model. It does indicate your model's wrong, but we know that's wrong anyway from George Box. Collinearity, big problem. In all of these regression models, this is a huge problem. This is a problem in your explanatory variable, your x's. What happens, it's basically a matrix problem. All of this stuff really comes through with matrices and inverses. If you have a collinearity, the matrices are not invertible, so you have problems. You have a redundancy in your x's. One of the x's is completely explained by the rest of the x's, or nearly completely explained. It doesn't have to be completely explained. And so that's a huge problem. This will cause the coefficients in your model to be wrong. We think studying should improve a student's score on a test. If I had a collinearity problem, when I fit my model, the model may say, oh, studying is a negative effect. That reduces a student's score. If I didn't know I had a collinearity, I'd be scratching my head. That makes no sense. A collinearity can really change things. It'll make things not very precise. So it's a huge problem. Linear regression that we typically do, huge problem. Logistic regression, huge problem, because it doesn't depend on y, it depends on the x's. If the x's have a collinearity, you've got a redundancy. It's very hard to detect. That's not hard to detect, it's easy to detect. It's hard to cure. But it can be cured. Influential points. Influential points are not necessarily outliers. Outliers can be influential. But what you can have is essentially a point that acts like a magnet, and it pulls the response surface to it. And that's not good. And because we can't see our data set in the 10 or 12 dimensions, we can't envision where that point is. It doesn't show up in any of our plots. There are diagnostics that look at the influence of any point. Essentially, they're deleted point diagnostics where they fit the model. They don't actually even do this, but it's equivalent to doing this. Fit the model without that point and see how things change. And each point has an influence, has a leverage and an influence. If it's an influential point, that can be a real problem because that's going to bring the line to it. More so than other data points. It could give you a very misleading fit. Okay, so we've done all this checking. We've got to address any deficiencies in the model. So if the assumptions aren't correct, we've got to do something. If you've got a collinearity problem, you've got to cure it. If you've got outliers, you've got to think about what are you going to do with your outliers. That's another slide coming. So we address this. It's an iterative process. And I've been teaching the regression and model building class each spring for the last few years. I'll bring up data sets, and they'll drive me crazy in front of the class. Class will sit there and laugh at me because I didn't anticipate this data set was going to have these problems. It's, okay, we've got to do this. No, we fix this. It creates some new problems. This is kind of an iterative process. And until we get a good, reasonable fit, we can't go on. You're never going to use a bad model. Well, I'm never going to use a bad model. So we refit. We go back to, there's lots of step 3s on this page apparently. Step 3, so step 2, refit the model, analyze, keep doing this until we've cured all the problems. Years ago, I took a fairly benign data set, gave it to a student for an undergraduate research project. It was modeling miles per gallon by some variables on cars, gross weight, horsepower, something about the size of the car. It's a nightmare data set to fit. The student was having trouble with it. I was like, this can't be hard. I know I've done this data set. It's very difficult. We went through this several times to find a model. Finally, stumbled across a model that was reasonable, made sense, and had no problems. It's not a race. Research comes slow often. Okay, so we've got an acceptable model. Doesn't mean it's good. Just says, okay, there's no problems. We have to assess the adequacy of the fit. So now, is it any good? And then we have to fine-tune the model. So often, when you do your planning stage, you say, okay, I'm trying to predict earthquakes in southwest Montana. And I have 37 variables I think might be relevant. And I build this model with 37 variables I thought were relevant, and it turns out probably some of them aren't. So we would like to knock out variables from the model that aren't important, aren't giving us any information about earthquakes. So fine-tuning is something we do. So that's basically what you do when you build a model. And we only use good models for making statistical inferences. If you've got any problems, in my mind, that's a bad model. Why would you use a bad model? So don't. So how do you tell if your model's any good? Well, an awful lot of the information about the model's fit is in something called the residuals. Residuals are the difference between the observed value of y and what you fitted for the value of y. Fitted is the predicted. So for all these x's, what did you predict y should be? That difference is known as a residual. If the residual is negative, so e is less than 0, then that says you're overestimating. Y hat's bigger than y. If the residual is 0, that's wonderful, then you fit it perfectly. Very unusual. If it does happen. If it's positive, then you're underestimating. So they tell you a lot. They're not all on the same scale, so we like to standardize them. So we use standardized residuals where you take the residual, you divide by its standard error. That makes them all essentially on a scale from -4 to 4, most reasonably. That's what we're going to look at. And these will tell us about the validity of the assumptions in a lot of models. They'll tell us where the model fits well and where it doesn't fit well. variation about the line, where outliers occur. So lots of information. And typically what we'll do is plot the standardized residuals versus the explanatory variable. Now any model you build will have residuals. There's all sorts of different types of residuals. I'm kind of focusing on the traditional regression residuals. But if you go to logistic regression, where you're modeling a binary variable, a variable that takes on two values, there's all sorts of residuals. There's different ways of looking at these things. So, problematic residual plots. Here's a residual plot that's indicating a bad problem. So, if we look here, all the residuals are positive. So, y is bigger than y hat in this region. From about, 6 down, you're underestimating y. Down here, they're all negative. You're overestimating. Then they're over here. So your model's not really doing a very good job. It's not estimating equally well throughout the range of the data. That's a problem. So we've got the standardized residuals here, the fitted values here. That's typically what we look at. If I see a plot like this is a simple case. I just have one x in the model, simple linear regression. That would be easy to fix. If I had 10 variables in the model, this often shows up. Then what I have to look at is residuals versus each x variable. It may be one x is causing the curvilinear nature of the residual pattern. So there's things we have to look at here. Residuals are critical. So, okay, there's the problem. What do I do? Well, if I add x squared to the model, so I add in another term, beta naught plus beta 1x plus beta 2x squared, it looks pretty good. There's just kind of a blob of data. I don't see that curvilinear pattern. So down here, some of the residuals are negative, some are positive. Throughout, some are positive, some are negative. So it seems to be fitting pretty well equally throughout the range of the fitted values. Now, these things can be tough on the eyes. You can see patterns if you look at these things for too long, which is easy to do. This might have another problem. But if you have a curved pattern in your residuals, that's saying your model's not doing a very good job. That's a violation of what we're after when we build a regression model. So curvilinear patterns are bad. Here's a pattern where I should have put the zero line in here. Essentially, some of the residuals in each vertical strip are positive, some are negative. But you can see there's kind of a funneling going on. So what that says is out here, there's more variability. You're not able to predict as well. Down here, there's very little variability. Your residuals are small. This is a serious problem. Violation of one of the assumptions. One of the assumptions in the classic regression model, here's 2x variables, is that you have equal vertical variation through the range of the x's. So over the fitted values, you should have the same vertical spread throughout. We obviously don't. We have funneling. It's known as a non-constant variance problem. Fixable. Standard transformation that will take care of this is a natural logarithm. What it often says is, and this is very common, this says basically as your y values got larger, you get more variability. Biological systems, that's typically the way it is. Mice, not a lot of variability in weight. Elephants, lots of variability in weight. So you see this in biology all the time. Natural log is a very powerful transformation. So when we're no longer modeling y, we're modeling the log of y. That's okay. It doesn't cause us any problems. It's still a linear model. It's still mice. So if I took the log of y and then I refit, I have a good residual plot. No pattern. Most of my residuals, these are standardized residuals, I would expect them to be between -3 and 3. If they're bigger than 3, depending on how much data I have, If I have less than 100 observations and I have a residual bigger than 3, standardized residual bigger than 3 or less than minus 3, that's indicating the model's not fitting very well. We'd expect it to be less than 3, between minus 3 and 3. But you can cure these things. Suggests a new model in each case. You can't always cure them. And often what will happen, in the previous slide, this is actually the same data set. There is a slight funneling here. It's maybe not that bad, maybe not worth worrying about. But because y is the same in all of this, this is actually a data set where y is the weight of a steelhead. This x is the girth of a steelhead, which is actually x2, and x1 is the length of a steelhead. And so there is a biological theoretical model, which this approximates. There's actually a better model out there. But taking the log cures the problem. So we do that. But you got to look at the residuals. You can see the outliers. They'll show up. Now these, I put in the lines at minus 3 and 3, depending on how much data you have. If you have 1 million points, you probably see a residual like 5. So, I mean, a lot of data, then you tend to get the extremes of the normal distribution, which these residuals will roughly fall. But this is saying, okay, you got a residual here. And so what we want to know is which point is it that our model's not fitting? Because this is saying our model does not fit that point. This, I don't know what data set this is. It doesn't look like 250 observations. I probably made that one up. So we're looking for those. You got an outlier, you got to do something with it. You got to think about it. Your model's not fitting that point. I've got an example I use in class where I'm trying to model percent body fat of adult males. And there's an individual in this data set that weighs 360 pounds, is very different than all the others. So maybe we throw that person out and say, well, we're really talking about, people that are not obese. That's what we want to model. So we might change our research on our target population to exclude that very strange point, but we should do something with it. So if I've got an outlier, first thing I'm going to do is say, is it impossible? The standard example I give in class, someone reports to me that they got a GPA of 4.5. It's impossible. I throw it out of the data set, I reanalyze. So that's the first thing you do. Is it a possible value? If it's not possible, is it a correctable mistake? A lot of times in the field we're writing in a lab book or something, we type something in wrong. We write things down wrong. We go back, we check our records. Can we correct it? If so, correct it. Refit with the correct value. If it's not impossible, nor a mistake, you're stuck with the point. So what we're going to do is we're going to delete it, and we're going to refit. So we'll throw it out, we'll refit, and then we're going to compare what happened with and without the point. So here we're seeing the influence of that point. If my model statistics dramatically change, it says that point's a real problem. And then, so if it's not influential, no big difference. You got a lot of data, you don't see big differences, keep the point, it's not causing you any problem. If it is influential, keep me in work. It's good to see a statistician. There are ways to deal with it. And even there are ways to ignore it by not throwing it out of your data set. I can make the model fit it perfectly. I can make any model fit any outlier you have perfectly. It won't give me any information, but we can keep it around. And then, the residuals, they can be very revealing. So here's an actual residual plot. I have this data set. So this is the clone zone. This is off of Leonard Stefanski's web page. He's a statistician at North Carolina State, does a lot of modeling. He's just figured out how to take a picture, scan it, somehow create a plot like this, and then create the x's and the y's that give you that residual plot. And he's done all sorts of things, any picture he takes. So this was one he, was very famous. So he goes around. He went to Iowa State, which has a big stat program, and he had this residual plot for him. So I don't know how to cure that one. I guess beat Iowa would cure that. So okay. So modeling. Really, you got to look at your residuals. That's what it's all about. We're not going to use the model till we've got a good fitting model. So, okay, now we've got a good fitting model. Got a lot of output. What does it all mean? So one of the important things is we want to assess the goodness of fit of a model. The common mistake is you look at your output and you look at the F ratio, and it's significant, and you think you got this wonderful fitting model. And it doesn't tell you that. All it says is that model's better than a model with nothing in it at all. So how does that tell you your model's any good? So we don't want to look at the F ratio. So we're going to want to fine-tune the model. So we've got some variables in the model we'd like to knock out. Almost every study of weight or body fat has height as an independent variable, a predictor variable. Height almost never has any relationship to weight if you have a good data set. You look at body measurements, circumferences, forearm, chest, thigh, abdomen, knee. They take all sorts of circumference measurements. Height really doesn't have any effect. It's explained away by all the others. Age is often in there. Percent body fat. Age really has nothing to do with percent body fat. It's body measurements. So we want to knock variables like that we thought might be important, but the data says really aren't. We'd like to knock them out. If we have a lot of variables, so maybe I have 37 variables in my model, that's a lot, and I want to screen them for importance. We want to use Occam's razor. The smallest model is the best model. So, what's doing a good job and as small as possible. So we want to screen for importance. So again, we don't want to use a bad fitting model, so we don't do that. Extrapolating beyond the range of data. Why is it so hard to forecast weather? Why is it so hard to forecast the stock market? We don't have any data on where the stock market will be in a year. That's why you can't do it. You can't predict the future. You can predict tomorrow's stock market pretty well. But you try to go long range on weather and stock market, predict the future, it's beyond the range of your data. You've built a model on the past history. So if I've got a range of data, say 1x, and it goes from 0 to 10, it's ridiculous to predict what happens at 20 or 30. I don't know that that same trend will hold. So don't extrapolate beyond the range of the data. And then we always have problems reporting a fitted model. There's lots of output. What's relevant? Now you're writing your paper. The analysis of variance table has no meaning in any paper that you should publish. You can summarize that. You really don't need to show people that. Okay, we're running out of time. So important, how do you measure the goodness of fit of a model? So how do you know that it's doing any good? So we've got no residual problems, no collinearity, no assumption problems. We're happy. It's good. Statistician gave us his blessing. R-squared is a common way we do that. And this is essentially looking at, and this only works for certain types of models. So that it's more complicated if you're not doing the standard regression models. But this looks at the proportion of variation in y that's explained by your model. So you've got a total amount of variation in the y's. How much is explained by your model? You can also think of it as it's the correlation squared between your observed y's and your predicted y's. It's got a lot of different ways of looking at it. The problem with R-squared, and why we have something else, R-squared adjusted, is R-squared goes up every time you add a variable to your model. So Mike Stickney's got a model for earthquakes. It's got 37 variables in it. He's got an R-squared of 0.8, and he puts in random phone numbers for all over the world. His R-squared goes up. And how do those random phone numbers affect earthquakes? They don't. But anytime you add a variable to your model, R-squared goes up. It has to. So R squared adjusted is an alternative. It's tweaked it. And what happens with R squared adjusted is it penalizes your model for having uninformative variables in it. You put in a bunch of uninformative variables, R squared adjusted goes down. It can actually be negative. So it's not really a square. But that's one way we look at it. And it's interpreted roughly the same way. Approximately what proportion of the total variation in y is explained by your model? It's bounded by 1. It's between 0 and 1. So an R squared, if you put it in percent, which we often do, of 80% is really good. R squared of 30% might be outstanding. Years ago at MSU, worked with some range scientists. The first model we fit had an R squared adjusted of minus 0.02. About as bad as I've ever seen. Well, it's as bad as I've ever seen. Built some models, got some explanation in there. We got an R squared adjusted of about 0.10, 10%. They were ecstatic. Nobody in the field had been able to do this. Basically hung clocks around cows' heads, and every time they put their head down, the clock started. Every time they brought it up, the clock stopped, and they claimed this was a feeding behavior. So we didn't publish anything out of that. Fine tuning, you got all this output, you got all these tests, t-tests. So if I want to drop variables, and you look at your output, you got this column of t-tests. Those are one at a time tests. If you want to knock one variable and only one variable out of your model, use a t-test and stop. You're done, walk away. Don't do one and then look at the refit and go, oh, I can get rid of this. That's cheating. That's data snooping. It violates all the rules of statistics. It's a multiple comparisons procedure. So we have something called the extra sums of squares F test. This is how you compare models of different sizes, nested models. It's very easy to do. You fit one model, you fit the other model, you compare their sums of squares, and you get a nice test. You can compare R squared adjusted values. It's a nice thing about this. Most statisticians believe that if you have two models and their R squared adjusteds don't differ by more than 2%, they're essentially doing the same job. So I got a model with 10 variables with an R squared adjusted of 80%, another model with 3 variables of 78%. I would say the 3 variable model is better. It's doing as well as the 80%, and it only has 3 variables in it. We want simple models. If you've got a lot of variables, we want to screen them. There's all sorts of techniques. BIC and AIC, Bayesian information criterion, Keiki's information criterion. Really good methods, work with all models. These are fairly modern, not caught on as well. Maximum R squared adjusted, great for regression. Malus CP, more sophisticated result. There's variable selection techniques. There are ways to screen your variables. Stepwise. A lot of people do stepwise. Terrible procedures. I believe in book burning when stepwise is in a book. So, forward is a disaster. The worst possible procedure you could ever use. Backward is okay. Stepwise is okay. It's kind of a backward. But they're not very good. These are better. And then you got to keep in mind when you do a variable selection, when you screen your variables, you're fitting a data set. That data set is going to speak pretty loudly. It's not representing the population. You've got to remember, you're fitting data, not a population. You don't have a population. You generally tend to overfit your models. The data tends to speak and tell you that's the model. We're not getting answers. We're getting, information. If a variable is really strong, if the signal's strong, it'll show up. If it's a weak signal, it may or may not show up. We don't need that. Hypothesis testing always a problem in statistics. So in conclusion, research shouldn't be rushed. Okay, we have external pressure. We have to publish. You got to get that publication to get tenured, promoted, and so on. That's unfortunate. That causes sometimes bad research. It'll be improved if you hire a statistician, involve a statistician. Chip and Suzanne and I pretty much work for free. We'd love it if you wrote us in the grants. Chip and I were talking about that. We really don't. like that idea since we're both department heads and have full-time jobs as that, but we're available. I've worked with people all over campus, be happy to do it if I can fit it in. I'm sure I can. You know, and then we want our research to be reproducible. So data speak loudly, but good science shouts. I mean, we need to think about the whole process. So that is my conclusion. Any questions? Oh. Any questions? Yes, Doug.
Sometimes you read about